Hello, class. Welcome to the lecture for Monday, April 6th. Um, there are two big events for the class that are happening this week, right? First, on Wednesday, April the 8th, you are going to submit your homework number 5. This is the homework on the pigeonhole principle, and that is due by midnight. And of course, you're going to email that to me. Just like you did the prior homework number 4. And so everyone seems to have done that successfully. So I think you're okay with the instructions for converting things to PDF files and emailing them to me. So I don't have to go through any details on that. And then also on Wednesday, April 8th, right, at Monday at 8:30, I will post the test number 2. Which will then be due by Friday at 8:30, April 10th at 8:30. That's when you will email your answers to test number 2, right? So you're just going to write your answers on a separate sheet of paper, or if you have the means to do this, you can print the test paper and write on there as well, and then again scan that and convert that to PDF, and then email that back to me by Friday, April 10th. So that's really what we're focusing on this week, those two things. I have already posted the answer key, so I'm recording this on Sunday, April 5th in the afternoon, but by the time you see this, the answer key will already be posted, or it's already been posted, so you may have already discovered it. But anyway, by the time you watch this lecture, the answer key will have already been posted for the sample test, right? Now, however, I just wrote the answers down, and I did not write, except for those last couple of problems on the pigeonhole principle, I did not write down complete solutions to the problems. I just wrote the answers down. And so I'm hoping that by looking at the answers, you can discover the solutions yourself if you weren't able to find the solutions without looking at my answers. Of course, you can log into my virtual office hours, right? My Zoom office hours on Monday, Tuesday, or Wednesday, for that matter, or Thursday, and ask questions about the solutions to the sample test or to homework number 5. However, what I'm going to do today, instead of resuming our lecture about inclusion-exclusion, we will do that on Wednesday. I'm going to go over some of the problems from the sample test since we don't meet face-to-face, right, and really don't have a convenient opportunity to ask me questions. I'm going to go over some of the answers to the sample test and try to give you more complete solutions. So that's what we're going to do in lecture today. On Wednesday, then, we will have a lecture for Wednesday, even though that is the day of the test. We will have a lecture for Wednesday, and so that's when we will resume talking about inclusion-exclusion. So I hope everyone is doing fine. I'm okay myself, doing great, and I'm looking forward to seeing everyone's test paper. But again, make sure that if you need to log into my office hours, the instructions there are posted in an announcement on Blackboard, and ask me questions, right? Okay. All right, so let's start looking at some of these sample test questions, and I won't be able to go over the entire sample test, but in the time allotted. But let's look at just a few key ones here, and so that hopefully I'll answer some of the questions that you may have about some of these problems. All right, so we're going to start with problem number 1. So that in this problem we have a standard 8x8 chessboard, and as you know, right, that typically has squares that are colored black or white in an alternating manner. So you have 32 squares of each color, right? 32 white and 32 black. But suppose we take off the restriction that the colors have to alternate, okay? Then in how many different ways can we color the squares of the chessboard if we still have 32 white and 32 black, but the colors do not have to alternate. So you could have in a coloring scheme 2 white squares adjacent or 2 black squares adjacent, right? Okay. So that's the question. We will, however, assume that the orientation of the board is fixed, right? So it's not that. We're not discounting rotations of the chessboard, right? Okay. Well, this is really just a partition problem, right? It's just what you've got is 64 squares, and here, right, that have to be colored, and you're really just dividing those into two different partitions, right? One partition that corresponds to the white squares, right, and then a second partition that corresponds to the black squares. So if we sort of make a very crude visualization of this partition, right, I've got to take some of my 64 squares, right, and I have to dump them into my partition here that I'm labeling white, right, and then I have to take 32 of the squares and I have to dump them into this partition that I'm labeling black, correct, right? So you're going to have some of the squares here, right, and 32 of them actually, right, and then you'll have some of the squares, right, that we're going to color black, right, put into the, you sort of visualize that as dropping them into this black partition, right, and so we select 32 of the squares to put into the black partition. And once the orientation of the chessboard is fixed, right, then the squares are you can identify the squares, right, by the row and the column in which a square appears. So I want to make it clear that the squares are distinct from one another, right? Okay, so there's sort of the setup, right, of the of what we're doing, right, to count this particular set, right? And so so again, this is merely a partition, right? We're taking the 64 squares of the chessboard, right, and we're dividing them into these two subsets, right? These two partitions. 32 will go into the white partition and 32 will go into the black partition. And so we saw in class, right, how to represent that number of different partitions, right? That is represented by this multinomial coefficient where you have 64, right, and then over 32 and 32, right, meaning that we've got 64 distinct objects, 32 are going into the first partition, 32 are going into the second partition. And remember, of course, this is shorthand for a particular number. This is called a multinomial coefficient, but the way you actually compute this multinomial coefficient, let me get the coefficients correct here, is 64 factorial over 32 factorial, 32 factorial, right? So that's actually the numerical value that corresponds to this particular multinomial coefficient. This, of course, is going to be quite a large number, so I'm not going to try to reduce this, all right? Okay, you might try to do that, but it's fine to leave it just in this form, okay? I want to point out, by the way, that 64 choose 32, 32 is, so that's a multinomial coefficient because I'm thinking of breaking the 64 into two partitions. But this is really the same as the binomial coefficient where we're taking 64 objects and choosing 32 out of them, right, as a subset, okay? Because when you compute this value, you get the same quantity here, right? You have 64 factorial over 32 factorial, and then 64 minus 32 factorial. But of course, 64 minus 32 is again 32, right? So this second factor in the denominator is still 32 factorial. So this multinomial coefficient, a multinomial coefficient where you have two partitions, is really the same as a binomial coefficient, right? Okay, where if you're taking 64 objects and breaking them into two partitions of particular size, that's the same as taking 64 objects and choosing 32 objects out of that for a subset. Okay. The reason that is the case, that these two things are equal, of course, is because when you choose from 64 the 32 objects that you want in your subset, then of course the remaining 32 objects that you did not choose automatically have to go into a second subset, right? The complement of the chosen subset. So really, when you choose a subset from a larger set, you're really partitioning the larger set into two partitions, right? The chosen set and then the complement of the chosen set. So that's why this multinomial coefficient and this binomial coefficient really are the same value. So if you wrote this as your answer to the question, then you would be correct, right? When you calculate these two quantities, you get the same number. Okay, so partitions, that's going to be kind of an important part of the test, right? And we're going to see other examples of partition problems in this sample test. Now, let's look at problem number 2. I'm just going to look at part A. Part B is more complicated because there are more options in part B. But let's focus for today on part A. So you can see the solution to part B, or the answer to part B, not the full solution, but the answer to part B is, again, on the answers to the that I've already posted to the sample test. So you can take a look and see if you can decipher how I arrived at this answer for part B. But if you have questions about that, remember you can log on to my office hours. All right, so let's look at part A. So here we have, this is actually a problem that I took from the book, so you may recognize it from the text. It wasn't in our homework, but it's in that same collection of problems that you turned in for homework number 4. So suppose we're going to create a football team, right, which has 11 players on it, and we've got 15 possible players that we can select our starting team from, right? And of those 15 that we can select from, we have 7 who can only play in the backfield and 8 who can only play on the line, right? Okay. So if we assume that a football team has 7 players on the line and 4 players in the backfield, that might be kind of a standard assumption, then we want to determine the number of possible teams, right, that we can create, right, from this 15 players. All right. Well, I think you can see how we would select a team, right? Okay. So our process of selecting a team, right, would be, we could say, let's start with the 7 players, right, that are going to be on the line. Okay. So we're going to choose those first. But we must choose those 7 from these 8 that can play on the line, correct? Right? Okay. So we have to choose 7 players out of 8, right? And so that's clearly a binomial coefficient, right? 8 choose 7. Again, this is also called a combination, right? So how many ways can we pick a combination of 7 players out of the 8 who can play on the line, right? Okay. And all right, so that would be our first step in creating the team, right? Choose 7 players for the line out of the 8 available. But then once we've chosen those, correct, then we have another step in creating the team. So the second step in creating the team is we have to pick the players in the backfield, right? So there are, how many was it? 7 players who can play in the backfield, right? And we have to choose 4 of those, correct? So after we've picked the line, then next we would pick the backfield, right? Well, you've got those 2 choices to make in sequence, so altogether the number of ways you can create the team would be 8 choose 7 times 7 choose 4, right? Because you have to make both of these selections, right, to get the complete team. So there it is. That's the answer to the question. It's the product of these 2 binomial, again, these are called binomial coefficients. If you want to write that out, but I'm not going to actually do the calculations, this would be 8 factorial over 7 factorial, and then 8 minus 7 factorial, right, which is 1 factorial, and then times 7 factorial over 4 factorial, and then 7 minus 4 factorial, which is 3 factorial. We could actually simplify this, do some of these calculations actually wouldn't be that large of a number, but I'm just going to leave it in that form. All right. Okay, so there's the answer to question number 2. All right, so let's get down here. I'm not going to look at number 3, but again, the answers are posted, so you can see what I got as answers for number 3. Now look at 4. So we haven't talked about circular permutations for a while because we've gone on to other types of problems, but I will ask you questions about this on the exam, right? So recall how we count circular permutations, and our part A here is an example of a circular permutation, right? I think we actually did this in the notes in the class at one point. We used this problem as an example. So it says, how many ways can we arrange 19 students in the class in a circle? All right. So remember, when you arrange objects in a circle, you get a type of permutation, but again, it's called a circular permutation, and the number of circular permutations here would be one fewer than the number of objects that you have, right? And then factorial. So the answer to A is going to be 20 minus 1 factorial, or 19 factorial. Okay. If we were just lining up the students from left to right, the 20 students from left to right, then you would have just a plain permutation, right? A linear permutation, and so then the number of ways you can arrange them in a line would be 20 factorial. But since you're arranging them in a circle, the number of ways you can arrange them in a circle is going to be less, and in fact, it's well, this many, right? Okay. Less by a factor of 20, actually. All right, only 19 factorial. All right, now B is also a circular permutation, but we are arranging different things in the circle. Okay, all right, because now in creating the circle of the 20 students, we want to have all of the majors sitting together. Okay. So they can be in any order together, but they all have to be together. So recall that in the class we had 12 math majors, 2 math teaching majors, right? Okay, and then 3 computer science majors, 2 data science majors, and then a philosophy major. Okay. So what you are really arranging in this object, what you're really arranging in this question, right? You can think of it as arranging the blocks of the students, right? Okay, you're really just arranging the majors in a circle, since all of the majors have to sit together. So you're really arranging this block of 12 math majors, this block of 2 math teaching majors, this block of 3 computer science majors, and then this block of 2 data science majors, right? And then the 1 philosophy major. So when we're creating the circle, we're really arranging 5 things, right? Okay, the 5 majors. Well, when you arrange 5 things in a circle, right, the way you can do that is, number of ways you can do that is 5 minus 1 factorial. Now, however, things get a little bit more complicated, all right? Once you have decided how you're going to arrange the majors in a circle, right, okay, so you might have decided where you're going to put, in what portion of the circle you're going to put the 12 math majors. But once you've made that decision, then you have to actually decide how you're going to arrange the individual students within the major, right? Okay, so once you've decided where in the circle you're going to put the 12 math majors, right? Okay, then you have to decide how you're actually going to line up the 12 math majors, right? Okay, and that is just a permutation of the 12 math majors. So to arrange the majors right, there would be 12 factorial ways of doing that, and you have to make that same decision, right, for every group of majors. So once you have again decided where the math majors are going to go in the circle, right, in what portion of the circle you're going to put the math majors, then you have to decide how you're going to arrange the math majors themselves, right? The individual math majors, and you can do that in 12 factorial ways. Now you have to decide how you're going to arrange the individual math teaching majors, and you can do that in 2 factorial ways, right? Then you have to decide how you're going to arrange the computer science majors. You can do that in 3 factorial ways. And then you have to arrange the data science majors, right? And you can do that in 2 factorial ways. And then the one philosophy major, well, there's really no way to arrange that person because there's only one of them, right? But if you want to be consistent, you can say, okay, I have 1 factorial way, which is 1 of arranging the philosophy majors in the class, right? So there's the final total, right, ways that you can put the the students in a class in a circle if all of the majors are going to sit together. Okay. All right. So you can look at part C now and look at my answer to part C, and you can see if you can figure out how I arrived at the answer that I gave for C. All right, let's look on to 5 now. This is really an important type of problem because the method that we use to solve 5A is going to we're going to use that same idea or sort of that same logic repeatedly in the next few problems. So I think it's really important to understand the answer to question 5, part A, because although that looks like a very specialized type of problem, the solution to that problem or the logic that we use to solve that problem is really quite useful in other counting situations. Okay. All right. So the basic question is, how many ways can we arrange the letters, right? In the incantation, the famous magical incantation, right? Abra cadabra, right? Okay. And so, well, how can we mix up those letters? That looks, of course, like a permutation problem. Initially, it is a permutation problem. But the complicating factor in this permutation problem is the fact that you've got repeated letters, right? So you really can't distinguish one A from another, right? Okay, and you really can't distinguish one B from another, right? Or you really can't distinguish one of the R's from another. So the answer to this question would not be just the total number of letters factorial. There are 12 letters in this word, but the ways of arranging the letters in this word is not 12 factorial because, again, when we have repeated letters, we cannot distinguish one of those repeated letters from the other. So you don't get actually 12 factorial different ways of arranging the letters in this word. Now, how do we think about this problem? Okay, well, all right, so we've done examples like this in class, so I hope you recall. Here's how I'm going to think of this problem. So when we did I write down 12 blanks here? Not quite. All right. So when we actually do rearrange the letters, right, in this word, we really have 12 positions, right, that we're going to fill up with letters, correct? Because there are 12 letters altogether in that word. All right, so I have to decide, right, which letter I'm going to put into each position. But notice that when I come up with the arrangement, of course, 5 of these positions are going to get filled up with A's, right? Okay, because I have 5 A's that I have to work with, right? So when I rearrange the letter, I'm going to end up with, obviously, 5 of the positions with the letter A in them. And let's write that down. So 5 of the positions, of the 12 positions that I have to fill up are going to get filled up with A's, right? And then, by the same token, right, 2 of the positions are going to get filled up with R's, because we have 2 R's to work with. 2 of the positions are going to get filled up with B's, right, because I've got 2 B's to work with. And then one of the positions is going to have a C, because there's only one C. One position is going to have a D, and one position is going to have an E, right? So rather than thinking of this as a permutation problem, I'm going to think of this as a partition problem, okay? And my partitions correspond to the distinct letters that I have in this word, right? Okay, and there are 6 distinct letters in the word abracadabra. So I'm thinking that I'm going to break some set, into 6 partitions that correspond to the letters, right, in the word abracadabra. Now, I said I'm going to break some set up into a partition with 6 partitions. What is the set that I'm breaking up into the 6 partitions? And the answer is it's the set of positions, right? The set of the 12 positions are what I'm going to partition into these partitions. So what I'm going to do is again break the set of positions into a partition with 5 positions in it. The partition that corresponds to the letter A. I'm going to put 2 positions in the partition that corresponds to the letter R. I'm going to put 2 positions that correspond to the letter B, right? So I'm going to put 2 positions in this partition, and then 1 position in each of these other 3 partitions that correspond to the letters C, D, and E. And once I know which positions are in which partition, then I will put that letter, right, into that position. So if I, for instance, put the positions 6, 7, 1, 3, and 11 into the partition labeled A, I've got to put 5 things in there, right? So if I put these 5 positions into the a partition labeled A, what that means is that in my arrangement of the letters, I would put A's in the corresponding position. So I would put an A in 6, I would put an A in 7, I would put an A in 1, I would put an A in 3, and then I would put an A in 11. And likewise, you fill up the other positions, right, with the corresponding letters, right, by again by looking at which positions go into which partition when you make a partition of the 12 positions, right? So really, the arrangements of the letters correspond to the way you can break the 12 positions into partitions where you get 5 letters in the first partition, 2 letters in the second partition, 3 letters in the 2 letters in the third partition, and 1 letter in the fourth, 5th, and 6th partition, right? Well, how many ways can indeed we break 12 objects into 6 partitions with these number of elements in each partition? That is just a multinomial coefficient, right? And so the answer here would be 12, and then 5, 2, 2, 1, 1, 1. That multinomial coefficient will tell me the number of ways of partitioning 12 objects, my 12 positions, into the 6 partitions where we put 5 in the first partition, 2 in the second partition, 2 in the third partition, 1 in the fourth, 1 in the fifth, and 1 in the sixth, right? Well, what is this multinomial coefficient, right? How do you compute it? It's so easy, right? It's 12 factorial over 5 factorial, 2 factorial, 2 factorial, and then a bunch of 1 factorials, which really are only 1, so I could really drop those from the calculation, but just for completeness, let's put it in. So there's the answer. That is the number of ways you can arrange the letters in the word abracadabra into different arrangements. And one of those corresponds to this, one of those arrangements correspond to this very famous incantation, right? Okay. So again, this idea, right, this partitioning idea, and particularly partitioning positions in a arrangement of things like letters is a very useful idea in counting. So it's going to come up in different counting problems that look completely different from this one, but we're still going to exploit this same idea again. Now, this part B is a now is a probability question, a pretty easy probability question, but I did want to introduce the idea of probability, right? So here we ask if we choose an arrangement at random. Okay, so our experiment here is going to be choosing one arrangement out of all these arrangements, right? We're going to choose one at random. So that's the experiment, and we want to know then what's the probability that we get a arrangement that begins and ends with an A. Okay, so our sample space, is all arrangements of these letters. Right, and the event that we're interested in is we get, when we pick a arrangement at random, the event that we are interested in computing the probability for is the event that we get a word that begins and ends with an A. Okay, so let's write this down here. So E, our event is pick an arrangement, pick an arrangement that begins and ends with A, right? And we want to compute the probability of that event. Our sample space, right, is all possible outcomes from this experiment. Again, the experiment is to just pick an arrangement at random. So the sample space here, the sample space is all arrangements of these 12 letters, right? And remember, just the basic idea of finite probability is that the probability of an event is going to be the number of outcomes in the event. That would be the number of arrangements that begin and end with A, right? And then divided by the size of the sample space here, right? That is all arrangements, period, whether they begin or end with A or not, right? Well, we already calculated here the size of this sample space. That's this quantity, that's this multinomial coefficient. By the way, I did compute that, and it turns out to be 997,920 if I did that right. So the denominator of this probability is 997,920. And now we have to compute then the size of the event, right? How many arrangements begin and end with A? Okay, so what is the size of this set E? Well, look, if you have an arrangement that begins and ends with E, right, what you're in effect doing here is putting an A in the first position, correct, and putting an A in the second position to start, in the last position to start with, right? So you can go ahead and assume that of the 5 A's that were available, right, in this list of letters, I already put one in the first position, and I put also one in the last position because I'm only interested in arrangements in words that begin and end with A, like this one, abracadabra, right? Okay. So what that means is to form the rest of the arrangement, you really just have to fill up these remaining 10 positions, right? And so you have to fill up these remaining 10 positions, which means you have to partition, to count this, you have to think of partitioning these 10 positions according to the number of letters available, right? But now you only have 3 A's available instead of 5, right? Because you've already placed one in the first position and one in the 12th position. So the size of E is going to be the number of ways you can partition 10 objects into, again, 6 partitions, but where 3 of the objects go into the first partition, 2 go into the second, 2 go into the third, and 1 go into the 4th, 5th, and 6th partition. And that's just this multinomial coefficient, right? 10 choose 3, 2, 2, 1, 1, 1. And you know how to compute that, right? That's 10 factorial over 3 factorial, 2 factorial, I'm running out of room here, 2 factorial, and then a bunch of 1 factorials, which are really only 1, correct? So you can just shorten this to 10 factorial over 3 factorial times 2 factorial times 2 factorial. Oh, so that's the number of outcomes, right, in the event that we get a word that begins and ends with E. So there is the answer. Y'all probably cannot read that, but it says 10 factorial over 3 factorial, 2 factorial, 2 factorial, all of that divided by this denominator, 997,920. Okay, so if you simplify this arithmetic, you can see there what the actual probability is. Remember, that's going to be a number between 0 and 1, right? Okay, so there's the probability that we get an arrangement. If we pick one at random, we get an arrangement that begins and ends with A. All right, now, again, I keep pointing out that this partitioning of positions idea is very important in counting, and we're going to use it again on as you've already seen in the notes in the class, right? We're going to use that again on a completely different problem, or a problem that looks completely different, but which really isn't completely different, okay? And that is this problem 6, which is how many solutions are there, integer solutions, actually non-negative integer solutions, because we want, in this case, we're specifying that the variables are all greater than or equal to 0, but we also want them to be integers. So how many non-negative integer solutions do we have to this equation? Okay, x plus y plus z equals 15. So for instance, one solution would be 15, 0, and 0, right? That counts because these numbers are all non-negative, and when you add 15 and 0 and 0, right, you get 15. But of course there are lots of other choices there for x, y, and z that will also give you solutions to this equation. So we want to know how many are there all together. And we're going to use this the same idea from problem 5 to solve this problem. Okay, let's pause there for a moment and see how we're doing for time, and then we'll come back and we'll look at the answer to this question. Okay, let's finish answering here, problem number 6. All right, so here's how we're going to visualize a solution to this equation. We're going to visualize it in a very unusual way. I'm going to think of my solution as corresponding to an arrangement of the letters or the symbols 0 and slash. Okay, so so let's demonstrate that as we did in the notes. All right, so here's just some arrangement. So this is, just think of this as a random, right? So here's an arrangement of the symbols 0 and slash, right? And I want you to notice there that I've got how many zeros all together. If I did this right, let's see, 1, 2, 3, 4, 5, 6, 7, 8, right? So I want you to notice that all together there, right, we've got, whoops, did I do that? I didn't do that right, okay. I'm sorry. Let me fix this. All right, so that's easily fixed. I want, the reason I'm counting the number of zeros there is I'm sort of thinking of the zeros as representing these, the 15 units here that I want my variables to sum up to. So I want to have the same number of zeros as this number on the right-hand side of the equation. So I think this works out right. I've got 5, 3, and 7, which is 15, right, altogether. And now, what the two slashes help me with is understanding how these 15 units are distributed amongst the three variables, right? Because these three variables have to add up to 15. So I'm going to think of x as corresponding to the zeros to the left of this first slash, and then I'm going to think of y as corresponding to the zeros there between the two slashes, and then I'm going to think of z as corresponding to the zeros to the right there of that last slash. So what I claim is that this sequence of zeros and slashes, notice that's 15 zeros and 2 slashes, this sequence of zeros and slashes corresponds to this solution to the equation. X equals 5, y equals 3, and z equals 7. That is indeed a solution to the equation, right? Okay, and so in fact, any sequence of 15 zeros and any arrangement of the 15 zeros and the 2 slashes, any arrangement I can convert to a solution to the equation. For instance, of course, you could arrange the 15 zeros, right, and the 2 slashes by putting all the 15 zeros first, right, in your arrangement, and then putting the 2 slashes at the end, correct? Okay, that would be an arrangement of these symbols, but that would correspond to this solution that I already wrote to the equation. This would correspond to x equals 0. Since we have nothing between the 2 slashes, that means x equals 15. Because we have 15 zeros to the left here, and then we have no zeros between the 2 slashes, so that means y is 0, and we have no zeros to the right of the slashes, so that means z is also equal to 0. So this sequence of zeros and slashes corresponds to this solution to the equation. So you see there's a one-to-one correspondence between the ways you can arrange the 15 zeros and the 2 slashes. There's a one-to-one correspondence between that number of arrangements and the solutions to the equation. So if I can count the number of ways of arranging these 17 symbols, the 15 zeros and the 2 slashes, then I will know how many non-negative solutions there are to this equation. Okay. But I know how to count the number of arrangements of the zeros and slashes, right? Because that's exactly what we did in 5a, right? Okay. So what we're thinking of is we've got 17 positions here that we want to break up into 2 partitions, right? A partition that corresponds to the 15 zeros and a partition that corresponds to the 2 slashes, right? So picturing it like before, right? I've got one of my partitions that corresponds to the zeros here, right? And I've got one of my partitions that corresponds to the slashes. Remember, you've got to have 15 things in this partition and 2 things in this partition, because you've got 17 positions that you have to fill up with these 17 characters. But look, now we know how to count partitions very well, right? That's a multinomial coefficient. So the answer to part A now is kind of obvious, right? Let's see, I've got 17 things, the 17 positions, and I've got to break them up into these 2 partitions, one of which has 15 things in it and one of which has 2 things in it. So I get the multinomial coefficient 17, choose 15 comma 2 as the answer here. This is 17 factorial over 15 factorial 2 factorial. So reduce that and reduce that multinomial coefficient, and you've got the answer. Okay, it's actually pretty easy to reduce that. Now, notice this multinomial coefficient, remember, would be the same as the binomial coefficient 17 choose 15, or it's the same as the binomial coefficient 17 choose 2. So you could have maybe expressed your answer to part A here in a slightly different way than I did on the solution sheet, because all these answers are equivalent. Okay, now let's also look at part B. This comes up in the homework. So this just is a variation on the first question, right? It says, how many solutions do we have where x, y, and z, instead of being just non-negative, where x, y, and z are greater than or equal to 2? Let me make I'm not going to go through the full solution here, but let me make a suggestion to you on how to answer a question like this. We're going to do some substitution here. So I'm going to change variables. In the original equation, we had x, y, and z. So I'm going to pick some new variables, and let me show you now what the new variables will be. So I'm going to pick a new variable, y1, and I'm going to let that be x minus 2. So notice that if x is greater than or equal to 2, right, and y1 is x minus 2, that means, notice that y1 has to be greater than or equal to 0. So this variable y1 just has to be non-negative, right? Okay, and then we're going to let y2 be y minus 2, and so that implies y2 is greater than or equal to 0, since y has to be bigger than or equal to 2, right? In this part of the problem. And then I'm going to let y3 be z minus 2. And since z is bigger than or equal to 2, this means y3 is going to be bigger than or equal to 0. All right, so now, what we're going to do is plug these three variables in to the original equation and change the equation. So xy plus z equal 15. That means that y1 plus y2 plus y3 has to be equal to 9. Okay, right? Not 15. And that's because of the way we defined y1, y2, and y3. So these have to add up to be 9, but now we have the condition that these three are not greater than or equal to 2, but only greater than or equal to 0, right? And now you can solve this. Now you can solve this equation, or you can find the number of solutions to this equation the way we answered part A here. Okay. So what is that? That is going to be 11. That's 9 zeros plus 2 slashes to separate the zeros, correct? And then choose what? The 9 positions that become 0, right? And the 2 positions that become slashes. So there's the number of solutions to this equation. And then the number of solutions to this equation will be the number of solutions to this equation where x, y, and z are greater than or equal to 2. So this is the answer to part B, right? Again, with this equation, right, you're thinking of how many arrangements do I have of 9 zeros and 2 slashes? 9 zeros to represent the 9 units, and the 2 slashes to represent, right, to tell us how many units go into each one of the variables. So you're breaking 9 positions up into 2 partitions. You're breaking 11 positions up, right? 9 zeros and 2 slashes into 2 partitions. 9 of the positions correspond to 0. 2 of the positions correspond to slashes. Of course, this works out to be 11 factorial over 9 factorial 2 factorial. Let's just make up a solution here to this equation just for fun. So it could be y1 is equal to 3, y2 is equal to 1, and y3 is equal to 5, right? Because 3 plus 1 plus 5 is equal to 9. So how does that give us a solution to the original equation, right, where x plus y plus z is equal to 15? Well, just add 2, right? Just add 2, right, to each one of these. Add 2 to each one of these values, right? So you would get x is equal to 5, and y is equal to 3 and z is equal to 7. Oh, yay, okay. That does indeed add up to 15, right? And notice, because you added 2, right, to y1, y2, and y3, notice that all of these variables are going to end up bigger than or equal to 2, correct? So every time you get a solution to this equation, you can translate it to a solution to the original equation. But we know how many solutions there are to this equation. It's this number. So that's how many solutions there are to this original equation with these conditions that x, y, and z have to be bigger than or equal to 2. Okay, now look, let's look at 7a because this is really exactly the same sort of problem. Okay, it looks different, but it's just the same problem in just kind of more colorfully stated. So we're asking here, how many ways can we distribute 10 Snickers bars amongst 4 children? Now, the 4 children are not identical, all right? So these are not quadruplets, okay? These 4 children are all distinct, all right? So we want to break 10 Snickers bars up into 4 children. All right, here's the way you do that. Look, let's let x1 be the number of candy bars for child 1, right? So that's the number of candy in our distribution. That's the number of candy bars that the first child gets, right? Okay, and then we'll let x2 be same thing, number of candy bars, except now for the second child, right? And then we'll let x3 be the number of candy bars, right, for the third child. And then we'll let x4 be the number of candy bars for the fourth child. And what do we know about x1 plus x2 plus x3 plus x4? How many candy bars do we have to distribute there? We have 10, right? So x1 plus x2 plus x3 plus x4, they have to add up to 10. So the number of ways of distributing the candy bars is the same as the number of solutions to this equation, right? And of course, no one's going to get a negative number of candy bars, right? So we know that x1, x2, x3, x4 are all greater than or equal to 0. So how many solutions do we have to this equation? You can use exactly the same logic as in problem 6. So you're going to end up with, and here's the answer that's given on the solution sheet, you're going to end up with this multinomial coefficient as your answer. 13 choose 10 comma 3, which of course is 13 factorial over 10 factorial 3 factorial. That turns out, by the way, to be 286 when you simplify this arithmetic, I think, if I did that properly. So there are 286 ways to distribute the 10 candy bars amongst the 4 children. Now you can use that answer to help you understand the answer to part B, which is a probability question. Okay, so you're going to end up with your answer in part B as a value between 0 and 1, right? Okay, so think about how you can use the answer to part B to give you this probability answer to the answer to part A to get this probability for part B. Actually, let's look at a probability question here now. So let's do number 8. Okay. This is the last one I'll do here as an example. The problems 9 and is there a 10? Yeah, is there a 10? Yeah, problems 9 and 10. I think I've got the solutions written a little bit more completely on the answer sheet. So you can probably look at the answer sheet and understand the answers to 9 and 10. All right, so let's look at this game, Tongits. So this is a real card game. And it's played with a 52 card deck, and oops, I left off there the number of players. Oops, that is there are 3 players, so that got left off, so I need to fix that. Ooh, okay, so there are 3 players, one of whom is the dealer. Okay, so when the hand is dealt, 2 of the players get 12 cards, the dealer gets 13 cards, and then a pile of 15 cards is left on the table. Okay, so so it's a 3-player game. A dealer and who's sort of he has a special role right in the game, but he's also, or he or she is also one of the players. And then you have just 2 regular players, right? So the dealer gets 13 cards, and the 2 players get 12 cards, and then there's this pile of cards right in the middle with 15 cards. So the first question is not a probability question, though. One just says, if we assume the players are distinct, in how many ways can the game start? All right, so if we have a player 1 and a player 2, and they're distinct from each other, plus the dealer, right, plus the pile in the middle, how many ways can the game start? Well, this is just a matter of how many ways can you partition the 52 card standard 52 card deck, right, into 4 partitions, right? Because you've got a partition corresponding to each one of the players. And the pile that's in the middle of the table, right? Okay. Remember, because the players are distinct from each other, right? We can distinguish between those 2 players, right? So we have 4 distinct partitions, right, for the 52 cards. And so how can we break 52 cards into 4 distinct partitions? According to the number of cards each partition gets, right? Well, it's going to be 50. It's going to be this multinomial coefficient, right? 50 choose 13, 12, 12, and then 15, right? Okay. So that's just a very straightforward counting partition problem. All right, now how many possible dealer hands are there? Okay, so how many different hands could the dealer possibly get, right? Well, that's also fairly straightforward, right? That's just a combination problem because the dealer gets 13 of the 52 cards, right? So that's how many subsets of 13 we can choose from this 52 card deck, right? Well, that's just going to be 52 choose 13, right? And so that is just 52 factorial over 13 factorial, and then 52 minus 13 factorial, right? Which of course is 39 factorial. When you compute this, if I did this right, you're going to get this huge number. It's 635,013,559,660. Can I read that number even? I think so. That's 635 billion 13,559,660. Okay, so a really large number there of possible dealer hands. All right. Now let's answer a probability question. So this is the number of possible hands, right, that the dealer could get, right? So we want to know what's the probability that the dealer gets a hand with 4 aces and all 4 of the aces, right, and exactly 2 hearts. So not more than 2 hearts, but exactly 2 hearts. Okay. So so when we so here's the sample space, right, for this experiment. The experiment is dealing the dealer giving the dealer 13 cards, right? Selecting 13 cards from the dealer. That's the experiment. So the number of possible outcomes for that experiment is this large number, right? So that's the sample space for the experiment, and the event that we're interested in is the event that the dealer gets 4 aces and exactly 2 hearts, right? So so the probability of that event is going to be the size of the event, right, or the number of hands that have 4 aces and exactly 2 hearts, divided by this total number of possible hands, right? Which is this huge number, 635 billion, etc., right? So this probability is going to be a fraction, and the denominator is going to be this huge number. We just have to figure out what the numerator is. That would be how many hands have exactly 4 aces and 2 hearts. How many dealer hands have exactly 4 aces and exactly 2 hearts. All right, so let's think about how we could construct such a hand, right? Look, to start off, the dealer gets all 4 aces, right? So you can go ahead and think of putting all 4 of the aces in the dealer's hands, right? So that portion of the dealer's hand is fixed, right? It's got 4 aces in it. And so all you're really left to do is to pick the other 9 cards, right? Okay, that the dealer's going to get, right? Okay, now how do we pick those remaining 9 cards? Because the 4 aces are already in the dealer hand, right? Well, look, when you pick the other 9 cards, you have to pick 1 heart, right? Because you want the dealer to have exactly 2 hearts, but the dealer will already have the ace of hearts. So the dealer will already have 1 heart in his hand. He has to get exactly 1 other heart. Well, how many hearts are left to choose from? Well, the ace of hearts is gone because that's already in the hand, right? So there's 3 hearts left, and we have to pick 1 of them, right, to put into the dealer's hand, right? Okay, so that the dealer gets exactly 2 hearts. So the first thing we can do in building up this special hand, right, for the dealer is pick the additional heart that is going to be in the dealer's hand, right? So now you have got 5 cards in the dealer hand, the 4 aces, and then the 1 additional heart, right? So that the dealer would have exactly 4 hearts. Now, once that's done, you've got 8 more cards left to select, right? To put into the dealer's hands. But, right, what's gone, right? Well, all the aces are gone, right? Because we've already put those in the hand. So you've only got 48 cards left to choose from, right? Okay. But these 3 hearts also are not available for selection anymore. One of them has already been put into the dealer's hand, right? The one we chose here. But the other 2 we cannot choose from them, right? Okay. Because we only want to have exactly 2 hearts. So really all that's left to pick the remaining 8 cards from is 45, right? Because the 4 aces are gone and you cannot pick any more hearts, right? So all the hearts are gone from consideration when you pick those last 8 cards. So in picking the remaining 8 cards to put in the dealer hand, you get you start choosing 8 cards out of only 45. So that is the numerator here in this probability, which I did not simplify, but it's 3 choose 1 times 45 choose 8. Let me try writing that a little bit better. Okay, so it's 3 choose 1, and then times 45 choose 8. Okay. So however that simplifies, it's that number divided by this huge denominator, right? That's the probability of the dealer getting this a hand that can be described like this, right? 4 aces and exactly 2 hearts. Okay. All right, well, those are the examples that I wanted to go over with you from the sample test, right? Okay, so and we made that in pretty good time, so that's good. I won't run over today. All right, so again, so the test will be posted on Wednesday, right, at 8:30 a.m. You will email your answers back to me Friday at 8:30 a.m. And your homework number 5 is due on Wednesday at midnight, okay? And so please log in to my Zoom office hours if you have questions, right? And about the homework or the sample test or anything else for that matter. All right, so I will see you again on Wednesday. We will have a lecture for Wednesday. We are going to resume with discussing inclusion and exclusion, right? We had gotten to the most general form of inclusion, exclusion in the notes from last week, so we're going to finish talking about inclusion, exclusion on Wednesday. And I will see you there. Stay safe, right? Be sure you're washing your hands, and now also be sure you are wearing a mask, right? Okay, when you are out amongst people. Okay, see you later.